Alrighty, here we go, guys. This is the first page of the notes. Everybody has seen this. We were talking about the direction of the electric field just being the direction that a teeny tiny positive test charge would go. Whatever direction it zips, that's the direction of the electric field. Here we were just trying to say, here's a positive 3, here's a negative 11. You can tell this is positive because the arrows point away. If you were to put a positive test charge here, it would zip away. If you put a positive test charge here, it would zip towards. So you can tell this one had to be negative. This has a bigger charge, so there's more arrows. This is a less charge, so there's fewer arrows. And then there's some pretty pictures that we had seen. Here are charges moving away from plates. Plates have constant electric fields, but we'll get to that coming up. So here's what you need to know. Basically, there's going to be two types of electric fields. The electric field due to a point charge and electric field due to what is created between charge plates. You're going to be expected to know the difference, and you're going to be expected to be able to use them both properly. Here's what you need to know. The equation for point charges is E equals K Q over R squared. And what this means to you is this means that the electric field decays as 1 over R squared. Here's like a little picture of a point charge. The field lines are represented here as those arrows. And if you look, as you get farther away from the electric field, the arrows get more spread out, which shows that it's weaker. But this 1 over R squared thing just means if you go twice as far away, the E field is a quarter as strong. If you go 3 times as far away, it's 1/9. If you go 7 times as far away, it's 1/49 as strong. And that's different than if you have an electric field between plates. The electric field between plates is given by the equation E equals F over Q. And this means that the electric field is constant between the plates. And here's a little picture of that. This would be a positive plate. This would be a negative plate. The electric field is still the direction that a positive test charge would go. So if we were to put a little positive test charge, let's see if I can do that real quickly. Boom, 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 boom. There we go. So if we put a positive test charge in here, it would repel from the positive plate and attract towards the negative one. And so the positive charge would zip in this direction. And that's why these arrows point in this direction. Now, the E field due to a point charge, let's talk more about that. The electric field at any given point depends only on the charge that's producing the field. This is just like Earth, the value of Earth's gravitational field depends only on the Earth's mass. So we talk about little g being 9.8, but we never worry about what the object being attracted to Earth is. Earth's gravity is still 9.8. And so this is just a little derivation. If we talk about force due to gravity, this is the old gravity equation. Force due to gravity equals mass. In this case, it was the mass of the apple times g equals this equation. The gravity equation, but mass of the apple cancels. So that's where we get G equals mass of the Earth, big G times mass of the Earth divided by R squared. So looking at this, you've seen this kind of thing before. Here's the gravity equation. Here's the electrostatic force equation. Here's the gravitational field. Here's the electric field. You can see they're the exact same thing. If you understand gravity, you understand the electric field from a point charge. So the electric field strength changes as you move through the field. Again, here's that little picture showing you that as you get farther away, the arrows get more spread out. So the E field gets weaker as you get farther away, which is different than if we talk about the electric field between plates. So looking at the electric field between plates, it was given to you as E equals F over Q, but you could just as easily rearrange that as F equals Q times E, which is really the same thing as F equals mg. And we use this F equals mg all the time whenever we're calculating the weight. And we always ignore the fact that the reason this works is because we're taking G to be constant. In other words, like if we go up or down a floor in a building, we don't worry about changing how far we are from the center of the Earth. We just keep G at 9.8. And so this is that same thing we're doing with F equals QE. We're saying that the E field's constant. And so if we look at the electric field between plates, if you look, the field lines are pretty uniform, meaning the electric field is constant throughout. And again, if we were to take a little positive charge here, and put it in between those plates, then it would repel from the positive and attract to the negative. But what we'd be saying here is that the electric field would be constant between here and here. Just like if we fall from one floor of the building, from the ceiling of a room to the floor, we don't worry about the gravitational field changing. As we go between a positive plate and a negative plate, we don't worry about the electric field changing either. And then if you look through the rest of the notes, here are some sample problems that would relate to things we've done. There's a null point question, and the rest of the stuff is spread out there for you. So good luck with it, and get at me on Remind.